So we are moving into chapter 3. Now we've actually already talked about some chapter 3 stuff because chapter 3 includes dealing with average atomic mass, which we did in lab last week. And so, we've dipped our toes into chapter 3 already. But we're going to get a little bit further into it. And as I mentioned Friday, with naming, we're starting to get into sort of the good chemistry, and then here today we'll actually deal with numbers. Great if you're a math person. So let's go ahead and jump right in. We've already talked about atomic mass a good bit, but I want to go forward and just make sure we're all on the same page in terms of what do we mean by AMU? What is all that stuff? And so the International Union of Pure and Applied Chemistry, IUPAC, has sort of set the definition of atomic mass as being an AMU. And so 1 AMU is equal to 1/12 of the mass of a carbon-12 atom. They chose carbon for a couple reasons. One, it's got an equal number of protons and neutrons. 2, it's relatively small and abundant. 3, more than 98% of all carbon in the universe is carbon-12. And so it's a pretty abundant isotope of a fairly abundant element. And so 1 AMU is sort of defined as that. Somebody asked last time, it might have been in lab, why don't we say that 1 neutron is 1 AMU and 1 proton is 1 AMU? Those do have slightly different masses, proton and neutron, and they're not one. A proton is 1.007 or something, and a neutron is 1.008, something like that. They're off a little bit because when atoms form and when those nuclei start to hold together, some of that mass is converted to energy so that nucleus can actually be held together. And that's where Einstein's equation of E equals mc squared comes in. We can figure out how much energy is required based on how much mass is lost in forming that nucleus. And so that gets into a little bit of nuclear chemistry, nuclear physics. We're not going to get there, but that's the reason why 1 neutron or 1 proton doesn't weigh exactly 1 AMU. Okay. And so another way to think about this relationship between AMU and carbon-12 is that 1 atom of carbon-12 weighs exactly 12 AMU. And I'm going to put ... here because it's as many sig figs as you want, because it's exactly 12 AMU. Okay. Now, up to this point, we've talked about individual atoms, individual ions, individual molecules. And in chapter 3, we're going to make this switch from this molecular scale, where we're talking about things in atoms and AMU, and we're going to switch across to what we think about as the macro scale, the world scale. And in the macro scale, we're going to be dealing with moles and with grams. It's much easier for us to measure out a mole of something than it is an atom of something. Similarly, it's much easier for us to measure a gram of something than it is an AMU of something. Okay. And so this switch requires us to come up with another way of talking about atomic mass other than using AMU. When we do that, we're going to be switching to what we call molar mass. To do that, we need to think about how many of a particular atom is going to be our unit, right? We talk about the mole sometime as the chemist's dozen. because it behaves just like a dozen, except it's a really big number, right? For a mole of something, it's 6.022, we'll cut it off at 4 sig figs usually, times 10 to the 23rd of whatever it is, right? We call this Avogadro's number. So if you sort of hear me say Avogadro's number, we mean this 6.022 times 10 to the 23rd. And so there are 6.022 times 10 to the 23rd whatever in one mole, right? We know that a dozen is 12, a baker's dozen is 13, a pair of something is 2, a gross of something is 144. And so, we have these terms for collections that are a specific number. It just turns out a mole is a really big collection, and it's got to be a really big collection because atoms are just so tiny. And so there are, in one mole of, let's say, nails, right? There are 6.022 times 10 to the 23rd nails. Right? That's a lot of nails. For one mole of copper atoms, Cu, is 6.022 times 10 to the 23rd copper atoms. Right? And hopefully this is a familiar concept to you. But if you haven't seen Avogadro's number before, it behaves just like a dozen, just like a pair, just like a score of something is 20. It behaves just like that, except it's a really, really big number. And the reason that we do this is because atoms are so incredibly tiny. Right? It's hard for us to measure out a trillion atoms, much less a single atom. And so we want to use, we need to use such large quantities so we can get them into some measurable scale. Okay. So, as I mentioned, we're going to convert from atomic mass. Now that we know something about the mole, we're going to talk to the molar mass. Right? And so the molar mass of whatever is the mass of one mole of that object. And it's in grams. And so when we think about molar mass, we think about grams per mole. If you didn't catch from the previous slide, the abbreviation for mole is just MOL, right? We don't abbreviate it too much because we don't want to confuse it with months or with meters. But grams per mole is the unit we will use for molar mass. We said earlier that one atom of carbon-12 equals 12 AMU. Well, now that we know that relationship between moles and molar mass and atoms and atomic mass, we can say that 1 mole of carbon-12 atoms is equal to 12 grams. Right? And so just like we did in chapter 2, talking about conversion factors, we can now use these relationships as conversion factors when we deal with converting between moles and grams, right? So we can turn this into 2 different conversion factors, either 1 mole of carbon-12 is 12 grams of carbon-12, or vice versa, right? 12 grams of carbon-12 is equal to 1 mole of carbon-12. We won't be using isotopes like this throughout the chapter. It's just, this is the definition of AMU and the definition of a mole, and so we need to be sort of rigorous about how we explain it. Right? For when we look at the periodic table, we saw that the molar mass, sorry, the atomic mass, that average atomic mass, is what's underneath the element symbol when we look at the periodic table. And so we can now say that 1 mole of any element has a mass equal to the atomic mass, or the average atomic mass, in grams. Okay. And hopefully now it's starting to be clear why we used average atomic mass instead of worrying about those isotopic masses. If I'm dealing with 6 times 10 to the 23rd atoms, and even if only 0.1% of those are a different isotope, that's still 6 times 10 to the 20th atoms, and that's still a whole heck of a lot of atoms. And so, dealing with the average allows us to ensure that we're getting a good value for the mass of our whole mole of atoms rather than any individual atom. Okay. Any questions so far about that switch from atomic mass to molar mass? Okay. So converting between the mass of a substance and the number of atoms in that substance. This is a nice little chart, a nice little diagram that takes us through these conversions. And so if we know the mass of a particular element and we need to go to the number of moles, then we're going to divide that mass by the molar mass. Our textbook uses this very script M for molar mass. It looks something like this, right? That's the molar mass of something. And it uses the symbol N for the number of moles. And we'll use that throughout this semester. And so little n is the number of moles, big N for the number of individual atoms. So let's say that we have 3.6 grams of, since we used it before, carbon-12. And I'm going to convert that to a number of moles. Well, I know if I have the mass of an element, to go to the number of moles, I need to divide by the molar mass. So the molar mass of carbon-12 is 12 grams for every 1 mole. Right? If I wanted to stop at number of moles, I could, but let's go on and figure out the number of atoms. And to go from the number of moles to the number of atoms, we're going to multiply moles by Avogadro's number. So there are 6.022 times 10 to the 23rd atoms of carbon-12 for every mole of carbon-12. If we go through and do some unit cancellation, grams of carbon in the top, grams of carbon in the bottom, moles of carbon on top, moles of carbon on the bottom, we're left with atoms of carbon. And if we plug that into our calculator, we end up with 1.8 times 10 to the 23rd atoms of carbon-12. So hopefully these conversions seem relatively similar to the ones we did in chapter 2. We're just using, introducing some new units rather than just converting between inches and feet. We're converting now between grams and moles. Okay. So let's do a couple practice problems. I'm going to give you a few minutes to work on these. There's 2 in a row here. And so if you finish on example 2, you can move on to example 3. If you haven't downloaded the lecture slides, they're on our Moodle page. And so feel free to download those and follow along, take notes. directly on those on that PDF. So I'm going to give you just a minute to work through this helium one, and like I said, if you finish, you can start on the zinc question. All right. All right, so if we start with 6.46 grams of helium from the periodic table, what do we get for the molar mass of helium?
4.003.
4.004, I think. Is that what we said? Helium's not one of those I use every day.
I think it's
4.003 in our textbook, so that's what I'll go with. And you know, for these where it's just a single element, it's not so necessary to include it in our unit, but it's good practice to go ahead and do that. Now it asks for moles, and we're already to moles, so we're just going to cancel our units. Grams cancel. We're going to do our calculation. 6.46 divided by 4.003. We get 1.61 moles of helium. And we're going to stick with 3 sig figs since that's the number of sig figs in our initial question. All right, so one that's a little bit more involved. How many grams of zinc are in 0.356 moles of zinc? This is going backwards, right? So we have 0.356 moles of zinc. And we need our periodic table again. 1 mole of zinc is 65.39 grams of zinc. This time our mole unit cancels and we're left with grams. So 0.356 times 65.39, 23.3 grams of zinc. All right, straightforward enough. Okay. All right. moving on from atoms, because it is rare that we deal with pure elements as chemists. We often deal with molecules or ionic compounds. And so moving forward, talking about molecular mass, that's where we take the total mass of a particular molecule. And remember, molecules are covalently bound. And are molecules made up of metals and nonmetals, or just nonmetals?
Non-metals.
Just nonmetals. And what do we call the one that was a mix of metals and nonmetals?
Ionic.
Ionic compounds. Absolutely. Excellent. So when we talk about the molecular mass, molecular weight, depending on who you're talking to, it's just the sum of all the atomic masses in that molecule. So we'll take our favorite molecule, H2O. Hydrogen, there are 2 atoms of hydrogen, and hydrogen has a mass of 1.008 grams per mole. And so we're going to take that. Well, this says AMU, but remember AMU and grams per mole are the same. And so we're going to take that, multiply it out, we get 2.016 grams per mole. Oxygen, there's only 1 atom, and so we get 16 grams per mole. So 16. And our overall molecular mass is 18.02 grams per mole. Remember our sig fig rule for multiplication and addition, for addition and subtraction, is that we round to the lowest number of decimal places. 16 just has 2. 2.016 has 3. So we're going to round it to 2 decimal places. So 18.02 grams per mole is the molar mass of water. Now, 1 molecule of water, of course, would weigh 18.02 AMU. But we rarely deal with single molecules of water. We often deal with things that are more like a mole. So let's do a couple more examples here. SO2 is a gas that's in exhaust, if your exhaust includes a lot of sulfur in it. SO2 is one of those gases, and then it can react with water to make acid rain. Caffeine, I think most students know and love. And so let's figure out the molar mass of these 2 compounds. Again, take a minute and work on those. All right, for sulfur dioxide, who's got something?
Is it 64.07?
64.07. And I'm okay if you put grams per mole or AMU, either one. I guess it asked for it here in AMU, so I'll leave it as AMU. Caroline, do you have caffeine ready?
I do. I have 194.2 AMU.
194.2 AMU. Yeah. All right. So again, we're just going to get real familiar with our periodic table and be able to convert from those individual atomic masses over to a molecular mass. One more. Here we have CH4. This one requires sort of two steps, right? Because we're going from grams to moles, but it's not of an atom anymore, like we did with zinc and helium. Now it's from this compound CH4 to moles. So who's got a good molar mass for CH4?
Six. Nope, go ahead.
Baird, go ahead.
I got 16.01.
Okay.
I think I'm using. Is there a? So we should be using the periodic table from the textbook.
Yeah. I don't really care where you get your periodic table from, as long as hydrogen is at least 1.01 or 1.008.
Okay.
Yeah. So I think that this would probably be 0.05. It's not going to change our answer a whole lot. Grams of CH4. Okay. Now it just asks us to stop at moles, so we'll stop there. 6.07 divided by 16.05. 0.378 moles of CH4. Now let's say I wanted to take this one step further. Let's say that I wanted to know how many atoms of hydrogen were present in 6.07 grams of CH4. I'm going to write out these two steps just so they're all in the same line here. And so let me just write it out here. How many atoms of hydrogen? All right, so my grams of CH4, methane, my grams of methane cancel. Where can I go now? I'm at moles of CH4, and I need to go to atoms of just hydrogen. Can I go ahead and convert directly to atoms? Nope. I need to convert to what first? Well, I know I'm coming from moles of CH4. But what am I going to?
You go to hydrogen atoms.
That's right. I need to go to moles of just hydrogen. Okay. And what is that ratio?
4 to 1.
4 to 1, absolutely. There are 4 moles of hydrogen for every mole of methane. And we know that just from that molecular formula. And then what do we use to go from moles of hydrogen to atoms of hydrogen?
Avogadro's number.
Avogadro's number, 6.022 times 10 to the 23rd atoms. We check our units cancel, moles of CH4, moles of CH4, moles of hydrogen, moles of hydrogen. We're left with atoms of hydrogen. So then we can do some math. And what do we get?
9.11 D23 atoms hydrogen.
9.11 times 10 to the 23 atoms of hydrogen. Absolutely. Absolutely. All right. And so that's, you know, for right now, for chapter 3, that's sort of as far as we'll go in terms of converting from one to another, from grams of a compound to atoms of an element within that compound. Right? That's about as far as we can go for right now. All right. Formula mass is similar to molecular mass, with the exception that when we talked about molecular mass, of course, we dealt with molecules. Formula mass is for ionic compounds, right? It's exactly the same idea. It's just for an ionic compound instead of a molecular compound. Generally speaking, I'll try to use the term molar mass so that it doesn't matter if I'm talking about a mole of a molecular compound or a mole of an ionic compound. We don't have to differentiate between the you know, whether it's a molecular compound that's held together with covalent bonds or an ionic compound that's held together with electrostatic interactions. But it's found exactly the same way, just for the sake of completeness. If we were to do BaSO4, right, the total mass of barium sulfate, the formula mass, would be 1 barium, so that's 137.3. Sulfur is 32.06, and oxygen is 4 times 16, which is 48.0. So if we add all this up, we get a 6, we get a 3, we get a 17, we get 217.36. With sig figs, that gives us 217.4 AMU, or grams per mole. Right. Again, it's just doing it for an ionic compound rather than for a molecular compound. Okay. As we continue, so now that we know how to go from, you know, the compound to the mass, what if we don't know exactly what the compound is? Or what if we don't know sort of how the composition of a particular compound is made up? This is especially pertinent for things like fertilizers, where we want to know how much nitrogen is going into the soil rather than how much of a particular chemical compound. But because nitrogen's a gas, it's very hard to just put nitrogen directly in the soil. It usually has to be bound up in some kind of chemical compound. And so we look at percent composition as a way of figuring that out. To calculate percent composition, right, the percent of an element is just equal to the grams of that element divided by the grams of the compound times 100. And it's always, we're always going to do this for grams of element and grams of a compound. Always going to do this for 1 mole of the compound. Right? And so for this molecule here, C2H6O, we're going to do this for all 3 elements. For carbon, for hydrogen and for oxygen. So the first thing we need to do, since we need to know the grams of compound in a mole, we need to calculate the molar mass for, this is ethanol, C2H6O. And so that's 12.01 times 2. That's 1.01 times 6. And that's 16 times 1 is 16. And so we get 46.08 grams per mole. So that's what we're going to use. So for carbon, what's the total mass of carbon? Well, we just calculated that here, 24.02. So, oops. Divided by 46.08 grams of our compound. Going to multiply that by 100%. We end up with just over 50%, 52.14. (52.13%) for carbon. If we do the same for hydrogen, 6.06 divided by 46.08 times 100%.
I got 13.15%.
Excellent. And then for oxygen, of course, there's two ways of doing this. We can do it just like we did for carbon and hydrogen, but all these percentages have to add up to 100, so we can also just subtract, right? We could say 100 minus 52.13 minus 13.15 gives us 34.72. Or we can do the math and say 16 divided by 46.08. So a couple different ways of approaching that problem for the oxygen piece. Okay. So let's do a quick example for phosphoric acid, H3PO4. We're going to do the percent composition by mass for hydrogen, for phosphorus, and for oxygen. I'll give you a minute to work on that. So just to make sure we're all on the same page, what did you get for the molar mass for phosphoric acid?
97.994.
Okay. Yeah. If you rounded that to 98.0, that's fine with me. 97.994 is good. So moving along. All right, Rosie, do you have hydrogen?
I got 3.09%.
Okay. Catherine, do you have phosphorus?
I'm doing it right now.
Okay.
Professor, Dr. Davis.
Yes, sir.
I just have a question. It's gonna sound really silly. I just forgot. For 100%, when you type it into a calculator, would it be 0.1 or like?
So if you're multiplying by 100%, we just need to multiply by 100.
Wait.
Um,
Oh.
Yeah.
All right. Thank you so much.
I got 31.6.
Give me one more sig fig.
31.61.
Excellent. Okay. Ashlyn, do you have oxygen?
I think so. 65.31.
Excellent. Yeah. If you just did subtraction there, you might get 65.30. Not a big deal. Rosie, was that a hand up or just a movement?
You answered it right away. I mean, I was just doing that because it wouldn't, yeah, that's all.
Yeah. So, if we have a difference in the hundredths of percent place, that's really a difference in the 10,000ths place. It's a really small difference. That's just a minor rounding error, rounding difference. And so, one way or the other is absolutely fine. Okay. All right. A way that we can use these percentages once we have them, or if we're just given percentages and we don't know what the compound is to work out the empirical formula, and then that'll help us on our way to figuring out the overall formula. The way we do this is to start with our percentages and to convert those percent by masses to moles so we can figure out the mole ratio. My guess is that this is going to take longer than 4 minutes for me to explain, so we will keep this for Friday, and we will call this a day. Any questions before we sign off here?
I actually do have a question real fast.
Go ahead, Nate. Oh.
This, I know I should have probably asked it sooner. But for our online book, if I purchased the Alex thing, did it come with the online book?
If you have Alex 360, which I think you probably do, it should come with the online book. And if you go into Alex, you should be able to, it should have an option for you to view the ebook.
Okay.
Let me see if I can get in here real quick to share my screen with you. So if you are over here in Alex, if you go over to the left, it should have an ebook option here.
Oh, I do see it now. Okay.
And so you should be able to go in and see what's what.
Okay, perfect. Thank you so much.
All right. Anyone else have any questions before we head out? Lily?
Yes. There was a document on our Moodle page listed with Lab 1, but it didn't like correspond.
Yeah. That was for my 400 level course. I put it on my wrong Moodle page.
Okay.
Yeah. So I got rid of it as soon as somebody let me know.
Okay. I just took a look at it and I was like, I don't really know about this.
Yeah. Yeah. That was my mistake. All right. If no other questions, then I will see you Wednesday for office hours, or if you schedule a meeting between now and then, I'll see you then.
Thank you.
Thank you. Have a
Thank you.
fantastic day.
Thank you.
Oh, I had another question. Is the quiz for Thursday going to be over chapter 2 materials or chapter 2 and 3?
So the only part of chapter 3 that it'll cover is that very first section that talks about average atomic mass. But it's mostly just chapter 2, atomic symbols, naming, and then average atomic mass.
All right. Okay. Thank you.
Sure.